All right, so we're going to look at a chain rule and we're going to look at it as an area analogy. And so we're going to start off reasonably straightforwardly because most people are familiar with the area of a circle. And so you know that the area of a circle is pi r squared. If we get a little bit more technical, we're saying that the area is a function of the radius. And all that means is, as you know, the radius increases or decreases, then the area of that circle will increase or decrease based on the relationship between the area and the radius, right? So what we can say here is if we take our circle and then we put like a ring around it. So we've got our circle, we're just going to put this sort of pink, thin, what's called an annulus around the circle. And so what we've done is we've essentially increased the radius by a little bit. So we're going to call this length here dr, and that dr represents a small increase in the radius. Now, here's the question I'd like you to pause and think about. So we're going to say to ourselves, all right, well, how does the area change as the radius changes? And what I'd encourage you to do is think about what is the area of that pink annulus. And hopefully you've had a pause and had to think about that. But the conclusion I hope you came to is if you could sort of unwrap that pink annulus and draw it out as a rectangle, you'd get a rectangle like this. And we can see that sort of the width or the height of that rectangle is dr, which is that small change in the increase of the radius. And then the length is 2 pi r. And you might be wondering, why is it 2 pi r? But I encourage you to think about the circumference of a circle. The length around the circle here is 2 pi r. And I know you're probably screaming and saying to yourself that this length around this inner part of the circle is different to the length around this part of the circle. We're going to take the situation where dr is really small. So this is an approximation, but if dr is really small, then it's a very good approximation. So if we just write down what we know, well, we know then that dA, which is the change in area, is equal to 2 pi r multiplied by dr. So let's just go back for a sec here. So yeah, we get 2 pi r dr, but if we just divide both sides by dr, we can see that the change in area with respect to the change in that radius is equal to 2 pi r. And hopefully you've done a bit of calculus at this point, and that should be screaming out at you, hopefully, as the derivative. If you come over here and were to take the derivative of a with respect to r, well, you bring the 2 down, so you get 2 pi multiplied by r, and then you reduce the power by 1, so you just get 2 pi r. Okay. And so now what we're going to do is we're going to start to incorporate this idea of the chain rule. And again, you usually get given a formula, but I want us to sort of intuitively understand how functions are chained together. So what we're going to do now is we're going to take this r value and we're going to vary that in terms of another parameter, which we're going to call u. So it's going to look something like this. So imagine we've got our circle. Here's another one. I just have to redraw it a little bit. And we're going to say the radius of that circle, so the length of this black line, is now a function of some other parameter, which we're going to call u. So we're going to call r, we're going to let r be equal to sine of u plus 1. And the reason I've just added 1 is because I didn't want the area of the circle to go to 0. So you'll see what I mean by that in a moment. But what we're going to do now is we're just going to sketch the graph of r equals sine u. So we're going to have our u-axis, which is going to be our x-axis, and then we're going to have our r-axis, which is going to go vertically. So that might look something like this. Okay, and there it is. So I'll explain the dr du part in a second. But if we just think about this line for now, this is the r-axis and this is the u-axis. And I'm guessing you've probably done some trigonometric functions before. So this is just sine of u plus 1. And this is over a period of 4 pi, because it's got 2 cycles, right? So this is how the radius changes as u changes. So this is how we're going to say it changes. The radius is going to increase up to this point here, and then it's going to decrease to 0, and then it's going to go up to here again, and then down to 0. Okay. And now what we want to do is we want to think about this dr du. So if we plot the derivative of that, so now it gets a bit tricky. We're saying now, how does the radius change as u changes? So for some change in u, so just imagine we could add a little bit to our line, our black line here. how does the radius change as the u values change? And I think you would agree again that that would be the derivative of sine of u. And if you've done a bit of this before, the derivative of sine of u is cos of u. So that's what we're actually just going to sketch here. And now we're going to get this situation. And we can see as our circle begins to increase, we can see that at this point here at the top, the radius is as large as it'll get. It'll get to a maximum height or a maximum length of 2. But the rate of change at that point is 0. Can you see how this point here is at 0? The derivative of r with respect to u is 0 at that point. So that means as it gets to that maximum height, it's neither increasing nor decreasing at that point. And that should make sense. It doesn't know sort of which way it's going. It's got to its max height, it's slowing down as it gets to its max height, and then it needs to come back, so it's sort of stuck there. So the rate of change of that point of radius with respect to that u value changing is 0. And then, so as we play it through, let's do another key point there. So this is when the circle is contracting, right? Because u is, our u axis is still getting larger, but what we're getting is that the circle is decreasing. And so at that point there, it's decreasing at its maximum rate. The circle is contracting most quickly right about there. Okay, and then we can just sort of run through the cycle a couple times. And so we end up with this situation. We sort of get this pulsing of the circle. And then we can stop there. But what we can ask ourselves is, all right, how did the radius change as u changed? Well, the change in the radius, well, the way it changed, and this is where it's tricky, was the rate of change, right? It was this sort of dark green function multiplied by du. So it's cos of u multiplied by du. Essentially just rearranging this. The change in radius is equal to cos of u multiplied by du. Very similar analogy to the previous one we did. Sort of make a small change to the radius by factor of u. I should say du. Okay, hopefully making a little bit of sense, because what we're going to do now is we're going to sort of use this information up here to come up with the chain rule. Okay, so let's have a look. If we just plug things in, so all we've done here is we've said, all right, r now is not just a function on its own. R is dependent on some other parameter or other variable u. So what we have is a of r of u. And this is what the chain rule is. There you can see how these are chained together. The area of the circle depends on r, but r depends on u. So you end up with a situation where we replace r with sine of u plus 1, because that is the radius, okay, in terms of u. So we get pi times sine of u plus 1 squared, just following this formula. And then what we get is, okay, well, we remember from before that the change in area is approximately 2 pi r multiplied by dr. But we know that dr is cos of u du. How does the radius change? Well, it changes as cos of u du. So we end up with this. Oh, there it is there again. So dr is equal to cos of u du. And so dA is 2 pi r multiplied by cos of u du, because dr is cos of u du. And now we know we're almost there. Last thing to say is, well, we know what this r is. We know this r value here. R is just sine of u plus 1. So if we replace this r with what r is a function of u, and we just divide everything by du, we get that dA du is 2 pi sine of u plus 1 multiplied by cos of u. Okay, and what a mouthful that was. But here's our conclusion, and this is essentially the chain rule. So let me just go back to this step for a second. We're saying that how does the area change as this sort of nested parameter u change? Well, it changes as 2 pi multiplied by sine of u plus 1 times cos of u. And so this is essentially the chain rule. The derivative of the area function with respect to u is the product of how the area changes with respect to the radius multiplied by how the radius changes with respect to that other variable u. And you can sort of see how they're sort of chained together and why it's sort of got the name, the chain rule. Okay, the last thing I just want to show you is this function. So what is dA du? So we're going to need a u axis now, and we're going to need a dA du axis. So let's sketch that and see what that looks like. I'm going to rescale a little bit. And this is what this function looks like. Okay, so this function here, dA du, is this. And so we say to ourselves, all right, well, what's going on here? How does this area function change as u changes? Well, apparently at this point here, when u is whatever this value is, then the area changes at a maximum rate. So let's just go back a fraction there. The area is changing at a maximum rate when that u value is right around there. Okay? When u gets to this value here, again, you can see that's as big as the circle gets. So yeah, the area is not changing at that point. Remember, it's sort of expanded to that point and then it's going to contract. So it needs to sort of, it's not increasing or decreasing at that point. That's why dA du goes to 0 at that point. And then we go through them. Down here is when it's contracting most quickly. And then we just play through. Again, here is going to be when it goes to 0. Again, it's neither increasing nor decreasing when it's at 0. And then, yeah, we play it through and we get this. And you probably just want to see the whole thing. So let's go back to the start. And you can get a feel for it. So yeah, I think that's pretty neat. Yeah, the formula for the chain rule is fascinating, but I think it's really cool to see sort of an area analogy. And someone in one of the previous videos wanted to see it as well. So shout out to them. This was a lot of fun to make, but it's hard work. So if you did find that interesting, give us a thumbs up, spread the word. If you need any private tutoring, feel free to get in touch. Always happy to explain sort of maybe how I make these videos as well, if you're interested. Yeah, all the best with your studies, and hopefully that explains a bit more of the chain rule. Good luck.